Hello everyone. Today I am going to present the paper A Load Framework for Calibrated Anomaly Detection in NIPS 2018. Anomaly detection is the problem of determining if a given point lies in a low density region given samples from a distribution. This paper concerns calibrated anomaly detection building on a classification framework for standard anomaly detection and show how to minimization of a suitable rubber loss produce density estimation only for anomalous instances, how to use pinpoint loss for contact control, how to use kernelized score efficiently. This paper did not propose a new best method, but would like to build a foundation for utilizing different loss combinations for calibrated anomaly detection. The presentation are going to go through 8 sessions: background on anomaly detection, introduction, loss for density sublevel set estimation, loss for partial density estimation, contact control via pinpoint loss, optimization without interval quadrature, relation to one class, HVMs, and conclusion. Let's take a look on background on anomaly detection. Anomaly detection is a problem of determining if a given point lies in a low density region given sample from a distribution. For simplicity, we can understand that given a normal data distribution and a test sample, we want to find whether the test sample belongs to normal data distribution or not. If it is not, it is treated as anomalous. There are two types of anomaly detection, that are standard anomaly detection and calibrated anomaly detection. Concretely, fit a probability distribution P over a measurable space S, typically Rn with the Borel sigma algebra, and a reference measure mu, typically Lebesgue, for which the density P is equal to derivative of P with respect to mu S. For standard anomaly detection, there are two ways we can pull low density anomaly detection. The first is the density sublevel set. Here, we are given alpha greater than 0 sample from P and test sample H. We wish to produce a function Cs mapped from H to 0 to plus minus 1 such that Cs is equal to 2 times of pH greater than alpha minus 1. Cs is equal to minus 1 means that test sample is anomalous. The second one is minimize my volume set or p-value. Here we are given Q in open interval 0, 1 sample from P S. We wish to produce a function Cs marked from S to plus minus 1 such that Cs is equal to high plus number of Ps greater than alpha Q minus 1. Cs equal to minus 1 means that test sample is anomalous. Alpha Q is the Q control of random variable of density scores P equal to PS, where S is sample from distribution P. The appeal of this E1 does not need to priori know the range of density values to beat a suitable threshold alpha. For calibrated anomaly detection, we wish to output a confidence in an instant being anomalous. Based on the density quantiles, we are given Q include interval 0, 1 samples from P, S, and wish to reduce beta function that match from it to uh, interval 0, 1 such that if PF less than alpha Q, beta function will equal to FPPS. Otherwise, eta includes interval Q1, where Fp denotes the cumulative distribution of P equal to Ps, and Fp Ps density contains corresponding Ps such that Ps greater than alpha Q, equivalent to Fp Ps greater than Q. In this paper, we present a loss function framework for calibrated anomaly detection. This builds upon an intent classification framework for the density sublevel set problem, which related the latter to binary classification of samples from the observed distribution, again no background distribution. This paper contribution to extend the framework in three ways. The first is so that's minimizing a class of proper loss asymptotically estimates the density for anomalous instances while ignoring the density for non-anomalous instances. The second is so how to obtain the quantized control by connecting this proper loss to a generalized bin-bone loss for control elicitation. The third is for a specific family of losses. We show how efficiently optimization can be performed with chronalized score using an idea from the field of point processes. This paper does not propose the best methods. This paper explains the characteristics of a family of losses and how to flexibly compile them for separation of statistical and computation concerns. The paper focused mostly on conceptual. We review a result of Stanford in 2005, which show how to cast density sublevel set estimation at a loss minimization. Here, we will study a loss framework for density sublevel set estimation. Let L is a function mapping from plus minus 1 or to or. E binary label loss. Example, logistic loss L EV equal to log 1 plus E power minus YV. Let F be mapping from S to R be real value scorer. Fix a probability distribution P over a measurable space S. Reference measure mu, typically Lebesgue. The risk of F is defined as formulation for RF is the risk for a binary classification problem of distinguishing positive observation from P from a negative background from mu, dependent of the risk on P, mu, and L. Based on the loss framework, we can show sub-level set estimation as a classification from the observation that suitable cost-weighted loss may show density sub-level set estimation. Let L from plus minus 1 plus R to R here any binary calibrated loss, example hint or logistic loss. Let's see in open interval 0, 1 be cost parameter. Cost weighted loss is defined as formulation phi. Distinguish claim proposition 1 that a bit any alpha greater than 0 and classification calibrated loss L for C alpha equal to proportional of alpha and 1 minus 1 plus alpha. The optimal scorer F greater than 0 equivalent to PS greater than alpha. We now observe that 4 can be used for estimating full density as well. To do so, we move from classification calibrated loss to the subset of strictly rubber composite loss. They are the basic loss of class probability estimation and certify for invertible link per mapping from interval 0, 1 to R with formulation 6. It claims that it's optimal to predict an invertible transformation of the positive class probability. One example is logistic loss and its link function per. The proposition 2 is given. Let I be a strictly rubber composite loss with link function per. The optimal scorer is equal to ratio transform link function per rad. Tackling calibrated anomaly detection poses several challenges. However, we need to first obtain the density p-value fpps greater than raw density value ps. The idea for this problem is start with some base scorer f mapping from S to R and compute a non-parametric estimate of p-value via the formulation 1. 2. Focus attention on density values lower than a threshold. The idea is the scorer must reserve the order of the tail values of the density So the scorer F mapping from S to R satisfying formulation 2 and will focus on the problem of partial density estimation. 3. Ideally, have the threshold correspond to a specified quantile Q in open interval 0, 1 of PS. The idea for this problem is find a way to automatically relate alpha to a quantile alpha Q to obtain the optimal scorer for partial density and just focus attention on the tail of the density. We using the wave function for entire density, then pay on that propose a partial density estimation. Wave function representation of a proper composite loss. That's a every shot loss with invertible link per se can be written as formulation 1. Example, if we put WC equal to C uh, times 1 minus C power minus 1 then corresponds to the loss, the logarithm loss. Proposition 2 so this loss estimate the entire density. Suppose we only want to model density value below some alpha greater than 0. We modify W to W bar as formulation of whole. The figure is the illustration of wave functions and corresponding losses and losses bar. The proposition for a claim with any alpha greater than 0 corresponding modifying loss functions, the risk formulation will be 16 formulation and the pace optimal solution is exactly the partial density estimation target. The base optimal solutions above have price that the loss will be non-convex. This is because a strictly proper composite loss has strictly increasing air power, meaning the cap version air power will saturate and thus be non-convex. This problem can be solved by naive remove the saturation using the partially cap loss defined as formulation 1. Proposition 6 is claim. Observe that when PSE uphold alpha, the pay optimal scorer no longer have complete flexibility in their reductions. Instead, they are claimed as exactly alpha. Intuitively, the problem of estimating such gap density is easier than full density estimation, but harder than partial density estimation. Thus, if a non-convexity is not an issue, it may be preferable to simply use C alpha strictly proper loss. On the other hand, we shall shortly see that partially proper loss can provide some quantile control. Example 7 is provided with the modified version of the LSEF loss for reference. We consider the last challenge that is achieving quantile control. Concretely, given a desired quantile level Q in open interval 0, 1, how can we automatically infer the suitable density threshold alpha Q? A natural idea is to incorporate the bin bond loss into our objective. For Q in open interval 0, 1, the bin bond loss phi function is given above. Lemma F is proposed to claim the phi function can be used. This idea can be generalized to any partially capped loss that build on some strictly proper composites with additional rho parameter at formulation 20. Proposition 9 is claimed that the rho star is the Q quantile of f star function. Example 10 below is given for demo that apply this technique on example 3. In practice, given same ensembles to optimize grid function, a natural strategy is to replace the expectation over P with its empirical counterpart and minimize the new rich function at formulation 22. The interpret in the formulation is complex and takes much computation. To remove that, we can use kernel absorption trick. A kernel absorption trick is proposed by Macular and Muller in 2017. Suppose we choose f from a reproducing kernel U-based space H with continuous kernel K, mapping from H times H to R. For gamma greater than 0, definition of the regularized empirical risk is at formulation 1. Now, suppose loss of minus 1 is equal to 1/2 times v squared. The paper showed that by Maxwell theorem we can get a more simple form as formulation 2, and consequently this risk is equivalent to formulation 3. Example 12 is the formulation of the risk function applied on example 3. Here we can see the formulation for kernel absorption treat with one class HVMs proposed by Skolkoff in 2001. The objectives are almost identical. The difference are that kernel absorption treat is regularized in a modified Hilbert space and that the regularization strength is not tied to Q. Time for conclusion. We presented a lot function framework for calibrated anomaly detection built upon an intent classification framework for density level set problem. We also extended this framework to a class of properties incorporated quantile control and discussed means of avoiding implicit quadrature for optimization. The framework also produced a close relative of the one class SVM as a special case, given a different perspective on the individual component of this method. Thank you for your attention.